Okay, yeah. So welcome to the 11th lecture on power system operation and control. Am I audible to everyone? Can anybody? Okay, good, perfect. I don't know. Okay. So we will be seeing this 11th lecture, and this will be our last lecture. I will see how much I can complete, but this is going to be our last lecture on optimization preliminaries. And from the Wednesday onwards, we will start our um, regular, or we'll come back to power systems and then solve our power system problems and see where these optimization methods will be used. We'll develop the optimization models which will be solved using these methods. And apart from that, few other methods we'll also see. Uh, so in the last lecture, we discussed about Newton's second order gradient method, and I hope it was clear to everyone. So again, I did not have pen today, so uh, just bear with me for a minute. And we saw this basic method for second order. We saw their advantages, disadvantages. We also saw about the interior point. We saw about how to solve it, the mathematical formulation, equation. We saw what is the importance of adding a Lagrange logarithmic function on a objective function, and because of that, it uh, ensures that the optimization product remains within the particular bound. It does not process that. So with this, I gave you this two-bus problem, and I hope did anyone try to solve this two-bus problem? So So I told to solve either by means you have to actually solve using all these three methods. But with just two iteration you can solve. And this is going to be your tutorial or the second tutorial from this Wednesday onwards. So it will be submitted on next Wednesday. So but so some basic of this problem is that I told you this how to basically write these equations. So this I have already shown you in the last class. I have derived it. So this is nothing but the just the power balance equation. I have just derived that and expanded it. Eventually, everything will come down to cos because there will be only three variables: PG1, PG2, and delta two. So eventually, it will come to this derivation. So these are the two equations. When you form the Lagrange function, it will be f1 plus f2 plus lambda 1 into this equality equation plus lambda 2 into this equality equation. Now, let me just cross check with everyone that are you guys able to understand this or not? So, if let's say if I have to solve this problem using first order Newton-Raphson method, so what will be the set of x values and what will be the set of u values? What all variables will come under control variables, independent variable, or U variables, what we have defined earlier, and what all variables will come under X, which are dependent variables here. Can anybody answer this? Anyone? Will be what? Will be control PG1 and PG2 will be control variables or the dependent variables? Independent, right? Yes. Uh, there is a small catch here. The catch is actually you can keep both PG1 and PG2 as independent variable. But here, what catch I am adding here is it is not necessary that you should add both PG1 and PG2 as a. Here I'm adding PG2 as a control variable and PG1 as a dependent variable. The catch here is generally in power flow, we have to keep one power generation value as a the slack variable. One generator bus has to be kept as a slack generator or slack bus. So therefore, one generator has to be specified as a slack load. And we know from the power flow that slack bus power is calculated at the end of the load flow solution. So we get the values of the slack bus solution after the convergence of the load flow, right? This is everyone is clear on this point, right? That the load flow, after the convergence of the load flow, we calculate the losses, we calculate the slack bus power, right? So the same logic, if you take here, because we have to first solve the the first equation, which is you have to assume one of the control variables equation value or PG2 you have to assume first. And then what you will do by assuming this PG2, you will take the derivatives in terms of dl by dx, and then you will calculate the values of the dependent values, which is PG1 and delta 2. And then you have will calculate after putting PG1, PG2, and PG and delta 2 in the equation, you will get the values of lambda 1 and lambda 2. Now, so basically, PG2 is going to be equal to 3. Let's assume I have just given a value that PG2 is 3. So how to get this PG1 and delta 2? Here you have to run a load flow. Without running a load flow, you cannot get the values of PG1 and delta 2. But it is not mandatory. If you are taking PG1 as U in U, then also you can solve it. So it is not necessary that you have to solve it using power flow, but I'm just giving an idea because there can be various other logic how we can keep the values. Right. So you can solve it by any method. So let's say, for example, let's say if you keep PG1 and PG2 both as a control variable, then what you have to do is you have to give initial guesses for both PG1 and PG2, and then by the assumption of PG1 and PG2, you will get the values of delta 2, and then you will calculate the value of lambda 1 and lambda 2, and then eventually you will calculate the mismatch of PG1 and PG2 using the derivative of dl by dp2. Right. So you can make any formulation in either of those cases. So it is up to you how you decide this expression. Right. So I'm not detailing it, but once you solve it in the assignment, you'll get the idea why I'm saying that there can be two different ways. So you can solve it while solving an assignment, you will get the better understanding of it. But I hope you got the basic understanding here. Now, if we have to solve it using second order method, we will take the complete set of variables PG1, PG2, delta 2, lambda 1, and lambda 2 all under one set, that is Z, and you can take the derivative or first order derivative of all the variables here, and you will also calculate the Hessian matrix. It will be like this. You will take the double derivative of all the five variables, and then you will get a 5 cross 5 matrix. And so you will get a 5 cross 5 matrix, and then eventually you will calculate the delta Z is by keeping it equal to, sorry, I missed a minus sign here. It should be a minus here. So 1 minus H inverse minus H inverse GZ, and you'll keep on updating based on the iteration values. And then once the data set is very small, then you can stop. So basically, you have to initially get an initial assumption first. You have to take an initial assumption here. So this initial assumption you have to take. and then you will be solving it using taking the derivatives of the complete Lagrange function. Again, you are going to anyway solve it, so it will give you a better understanding. Once you solve it, you will get the feel of it. Just wanted to give you a brief overview before we go. Okay, so yeah, it is there, but I'm not going into detail here, but I'm assuming that when you solve it, you will get the idea of it. Okay, now let us start our another topic, which is linear programming. And this linear programming, or let me just keep it in a highlighter. Okay, so linear programming is actually what is the use of linear programming first? Why do we want to learn about linear programming? Why not the previous methods? What we saw, those methods were based on derivatives, and those methods can actually solve both linear and non-linear type of problems. But there is there are before these methods got developed, the nonlinear solution methods, or basically we saw that interior point method, which was the best method which can handle inequality, was developed in 1984, right? So obviously before that we did not had any method which can confirm the convergence and also confirm the optimality, so and ensuring all the limits are bound. So therefore people before that, before 1984, people actually developed linear programming methods. There are different methods which actually dedicatedly solve linear programming method. And what do I mean by linear programming is basically an optimization formulation where both objective function and the constraints are all linear. There is no non-linear term will be there. So everything will be linear, right? Now, what is the importance of this linear programming in power systems or in any uh, application you take wherever optimization is required? The linear programming actually is, there are two three advantages. Let me just quickly tell you the advantages. One is when the problem is linear, you can get a global optimal solution, right? As soon as the problem is linear, it will be a global optimal solution. A solution can either be means there will be only one minima or maxima. If either you are going for minimization or maximization, so there will be only one minima or maximization with whichever problem you're solving. So that is the one biggest advantage. Because problem is, let's say if you are solving any problem, let's say even power system problems, if I talk about in a simple sense, uh, like if you have more than one answer for a optimization problem, then what will happen is that if you have generators, let's say PG1 and PG2, if we take the same example, and if you have more than one solution for that, because you can see in the equation, in the power balance equation, on the right hand side there is trigonometric uh, terms are there, cos delta 2, sin delta 2. Do you remember that? So because of those trigonometric constraints, this problem is non-linear, and there can be multiple solutions of PG1 and PG2, right? And when we have a multiple solution of PG1 and PG2, how can you tell a generator that which solution is perfect or which solution to settle at? So this is difficult, right? Practically, it is not possible. For example, if I take let's take any other problem. Let's take any car automobile manufacturing industry. There, if you see in automobile manufacturing industry, you have a conveyor belt where cars are means the skeleton of car is placed, and then that car goes onto the conveyor belt, and gradually robots or automated robots are there which actually installs all the components of the car one by one in the conveyor belt. Now, for that also, there is an optimization problem which decides which robot will install which equipment first and which will be installed afterwards. So there is an optimization problem for that. Now, if you have an optimization problem which is again of a nonlinear type, which solution will you settle at? It is difficult, right? We cannot, because for all those nonlinear problems, what we saw just now, in all these problems, we cannot guarantee a global optimality. We cannot guarantee that there will be a unique solution. There will be a multiple solution. So therefore, people still today, even in power systems, although we know power systems are non-linear, and in general, any optimization problem or any practical problem you take from any domain, every problem is non-linear. But because of this issue of multiple solutions, it becomes really difficult to settle down at a single problem solution. And this is a very big issue in the nonlinear optimization problem. And for example, I can also talk about stock exchange. Let's say talk about stock exchange. So in stock exchange, whatever optimization problem they run to settle down all these stocks, there also people method which is adopted is actually a non-linear. If you see a problem in a broad sense, it's a non-linear problem. But again, it's their money is involved, economics is involved. So let's say if one solution is there, it will favor some persons and it may go against some person, and another solution will favor some another set of persons and it can go against some another set of persons, right? So you can imagine if money is involved, how can you decide that how will means there will be a big fight, right? Uh, how to settle down on a single solution. Therefore, considering all these points, linear programming still makes a big sense because mathematicians still do not have answer for nonlinear optimization problem. There is no guarantee that you will get a unique solution, and or there is no guarantee that you will get a single global optimal solution. There is no method yet. So we are still lagging behind in those areas, and I can tell you frankly that if you are able to do it, because this is a very big research problem, if you are able to do it, you will definitely get. I'm not sure how many of you know this or not, because Nobel Prize is not there in mathematics. Nobel Prize is there only in economics. So most of the people solve mathematics problem in terms of economics. So if you are able to guarantee that, then probably you will get a Nobel Prize in economics if you are able to solve it. So this is the very big research problem which is still unsolved, and there is no method which can guarantee as of now. So for this is specifically for mathematicians who are still struggling to find the method. And once they solve it, then obviously all the problems will be resolved. So, as I told you before, that in reality, all practical problems are non-linear in nature. So, there is no practical problem, which is linear. So, therefore, this is even more difficult. So, therefore, people, what they do is they simplify their non-linear problem. We will also see how we simplify our power system problems into simpler forms or a linear form, and then we solve that linear problem for all of our power system applications. So practically, if I talk about from the system operator point of view, from power exchange point of view, for expansion planning point of view, every problem is actually linearized and then it is solved. So practically, no power system problems are solved in a nonlinear form. All are solved in a linear form. So we'll see gradually later on in the course that how this non-linear is converted into linear and how it is solved. But this is the main reason why we still go for linear methods. And linear programming is very popular, and it is basically the method which I'm going to tell you actually today is was developed 50 years ago. So there is nothing new which I'm going to teach. It is a very old method, but it is a very smooth method and it solves the problem in a very perfect manner, and it gives you a solution in a very fast way. So again, I already mentioned why LP. So obviously, speed accuracy trade-off is one such requirement. We also want simplicity. We also want very effective solution. We want low cost solvers. So basically, solution. So even I can tell you, linear programming can be solved just in Microsoft Excel. So you can solve the linear programming in Excel, and it's a very simple toolbox which is also there in Excel. You can solve it there. So this gives freedom to many people of various domain to formulate their problem in a linear form, and they can solve it in Microsoft Excel as well. And if they have better tools like MATLAB or even better solvers, they can obviously solve bigger problems. But still, MATLAB does the job in a perfect manner. There are few other methods like successive applications of linear programming, SALP. These can actually solve nonlinear problems into by converting them into linear form, but these methods are still not. Uh, these methods also do not guarantee global optimality. We can solve nonlinear problems by linearizing it, but still guarantee of linear global optimality is still missing in that. Right. So let us see the reason behind the simplicity and high speed of LP. And this is basically, let us see using a two variable problem, which is maximization of 3x1 plus 5x2, where 3x1 plus 5x2 must be less than equal to 18, and x1 and x2 can vary between 0 to 4 and 0 to 6 respectively. Now, if we have to formulate it in a graphical representation, I hope you got the idea. Probably you got from your tutorial assignment, you must have observed this that for drawing this graphically, we have to draw a x-axis where x1 will be there, x2 in the y-axis, and then you have to draw all the lines x1 greater than equal to 0. So that means there will be a mirror in this side, x2 greater than 0, that means mirror will be there on this side. X1 must be less than equal to 4, that means mirror is going to be here, and then x2 should be less than equal to 6, the mirror is going to be here. And then we know that 3x1 plus 2x2 must be less than equal to 18. And if you draw this line, this middle line will come and mirror will be here. So you can see that this area is going to be the feasible region of this optimization problem, right? And in this, also another important point from the linear problem programming point of view is that all the solutions used in linear programming problem will always lie in the on the corners of this bold black dots. So the optimization solution or optimal solution will only lie in these corner points. There will never be a solution in between this region. There will be no solution neither on these lines. There will never be a solution. So the solution is always on these corner points. Now, once we know this basic understanding that the solution always lie in the corner points, and we know that we want to maximize this objective function 3x1 plus 5x2, if you just draw the contours of it and go in the maximization side, and then you will see whichever points is coming in the direction, the last point will be the maximum solution. So for example, this line what I have drawn is actually the contours of this 3x1 plus 5x2, which is the objective function. And you just keep on going in this direction. And whichever point is last coming here, and this point is going to be your optimal solution. And rest all is the all are feasible solutions, but they are not optimal. So you will always find single solution which is optimal, and this gives a global optimal condition that okay, there's always going to be only one solution in this problem, right? So with this graphical representation, you got the idea that this problem becomes very simple because there is no solution which is lying in the center. So whatever is the feasible region, solution always lies in the corners. And because it's a linear problem, and in linear problem you will always draw lines. And if you're drawing a line, that means basically there will be some corners because there is no curved line because it is linear. So there will always be corner points, and you just need to check the corner points. And if you can imagine, if there is, let's say, if a problem is really huge, if there are a lot of variables and lot of constraints, you can imagine that these corner points will be very less. Why? Because the problem is big and there are a lot of constraints. So automatically, because if there are a lot of constraints, the number of corner points becomes very less, and even the solution becomes much faster. So to satisfy all the corner points or to satisfy all the constraints, eventually the number of corner points are very less, and this makes the problem or the LP problem very simple to be solved. Right. I hope everyone got the idea. We'll see how this is solved. There is an algorithm to it, and we'll see that how it is solved. Optimization problem. You have to actually first convert this problem into standard form. So sorry, I forgot the pen, so I'll just write it like this. So this is the standard form, and this standard form is also known as canonical form. We also say this as the canonical form. So what do we mean by canonical form is first you have to convert the optimization problem into minimization type. That is one criteria. Let me just tell you, and I've written here standard, or you can also call it as canonical form. So here you can, so to convert an optimization problem into a standard form, what you have to do is you have to convert all the constraints into equality type. There should not be any constraints of inequality type. And for all the constraints, your right hand side, which I mentioned B1, B2, must be non-negative. So this is an important observation which you have to mention here. So for example, let's say if there is a constraint called 3x1 plus 4x2 less than equal to 50. So you will add a slack variable, and adding a slack variable ensures makes the problem equality. And when you make the problem equality, then S1 will be greater than equal to 0. So the slack variable should always be greater than equal to 0. If a constraint is of greater than equal to type, then you will add minus S2 here. And then again, S2 will be greater than equal to 0. And you have to ensure, because here both the right hand side are positive, so you do not have to worry about. If let's say if it is negative, then you have to multiply minus one sign on both the sides, and then you will add a slack variable. Right. So you got the idea. This is the first step for the conversion of any LP problem into a standard or LP or a canonical form. The next is all the variables must be non-negative. Even variables should not go into negative. So let's say if a variable is there which can take from minus 10 to plus 10. So what you can do is you can convert a variable into two. You can split the variable into two variables, which is xi1 and xi2, where xi1 can take any value from 0 to 10, and xi2 will also take any value from 0 to 10. And you can imagine, you can observe here that if this xi1 is from 0 to 10, then xi2 will be 0 because it doesn't make sense. And if xi1 is 0, then xi2 can take till 10, 0 to 10. So the minus sign is there, so it is obviously taking from minus 10 to 10. So this is the way you split a single variable into double-sided variables, and you ensure that all the variables must be a non-negative form. Right. So this is the second condition. And the third condition is the optimization problem must always be of minimization type. If you can never have an objective function which is of maximization type in this method. So for ensuring this minimization type, if a problem is maximization type, just multiply the objective function with minus one. It will automatically convert that optimization problem into a minimization type. Right. So with this, let us see some typical characteristics of LP model. One is obviously the number of variables. Whenever so to solve any problem with this condition, if let's say number of variables are equal to number of equations, let's assume n is equal to m, then what will happen is whenever n is equal to m, then you do not need optimization. You can directly get the solution, right? Only when number of variables are more than m, or that is number of equation, you need an optimization problem to arrive at a single solution, right? Now, if I tell the reverse thing, if let's say number of variables are less than the number of equation, what happens in that case? Can you guess? If let's say number of variables are two and equations are three, how will you solve it? Or there is some issue? Yeah, infinite or multiple depending on the number of equations and all, there will be multiple solutions, right? Exactly. So if the number of variables are less than the number of equations, then there is always a multiple situation of multiple answers or multiple solutions, and we call it as a redundant case. So that is a difficult thing to resolve. Which actually you will study in the computer aided power system course. When you study state estimation, you will observe that how this creates an issue, and how to resolve these issues. So you will see that in that course in power system how we resolve that. And similar logic you can apply in power system also to resolve those issues. So whenever n is equal to m, then obviously you can solve it. If n is greater than m, then obviously we cannot solve it and we need some sort of optimization. And adding the slack variables, what I told you just previous slide, I mentioned about adding a slack variable for corresponding to this equality and inequality constraints. This adding of slack variables basically makes the problem equal to n is equal to m. And what we do is we actually fix some variables. Like let's say if n is greater than m, we what we'll do, we'll fix some of the variables, which is n minus m number of variables. We'll fix them a priori, and we'll solve the remaining equations and remaining variable by just a unitary method, or solving a simple equation method. Right. So this is the simple way of doing it, and we'll see there is an algorithm how we fix it and how we solve it. So we'll see probably in just one or two slides. Now, the logic for implementing this algorithm, or fixing these variables, how to decide which variable to fix and which one can be free and can be calculated from solving the solving set of equations. So here what we say, there is a concept called basic and non-basic variable, and we call non-basic variables which are fixed a priori. So basically they are fixed already, so they are non-basic. And basic variables are variables which are free and it is obtained from solving set of equations, right? So this is the nomenclature. Non-basic, just keep this in your mind. Non-basic variable means fixed variables, and basic variables means the variables which are free to take any value by solving set of equations. So basically, whichever solutions satisfy all the equations without any violations, we say that the solution is basic feasible solution. Right. So this is the way we name it. And here, whenever we say basic physical solution, that means the solution should be feasible. And if it is feasible, then it will be optimal. So this will be clear once we solve a seed algorithm as well as solve the optimization problem. So the algorithm, what we are going to see in this course is simplex algorithm. And this is one of the most popular algorithm which is used for solving linear programming method. And in most of the uh, uh, toolbox what we have, they use this simplex algorithm for even MATLAB uses this simplex algorithm for solving and linear programming problems. So we are going to see the algorithm of this and how it is. We will also see one example and we'll see how it is solved and probably we'll also get one tutorial on it, how we can solve it. And this the tutorial will be based on a power system problem and that will give you more connection of linear programming problem. So basically, what it does is this algorithm, it actually, as I told you before, that the linear programming problem has an optimal solution only at a corner points. And if you just keep on searching for, looking for all the corner points, if let's say a problem is defined in such a way that there can be various number of linear corner points, if you have uh, many variables and many constraints, for set in such a way that there are many corner points and it can be huge also at times. So if you go on searching all the corner points, then it will be really difficult practically to get a answer for a big problems, right? So basically you need to search for corner points in a systematic manner and so that you arrive at a solution at a very fast pace. So this we are going to see how we actually see these search these corner points and to arrive at a solution at a very fast pace. This we are going to see in this in a while. This is the idea of actually simplex algorithm. So the idea here is we will first fix the non-basic variables either to their lower or higher limit as per the criteria. I'll tell you the criteria in a while. And once you fix that variable, you only have basic variables and number of equations are also equal to the basic variables. And you just need to solve those basic variable equations and you'll see if all the limits are satisfied, then you say that the optimal solution is achieved. And you, before solving that, you also convert your optimization problem into a canonical form. As I told you before, for converting canonical form, you have to add slack variables. And here we add slack variable even to the equality constraints. And when I say equality constraints, obviously, if you add a slack variable to equality constraints, these are going to be zeros and known if any. So obviously, you know the if you add a equality slack variable on equality constraint that will be equal to zero. This again we will see in a practical example and we'll solve it in the class and that this will give you a better understanding. Now let us see the algorithm of it. It is going to be a bit confusing because it is like that. It is going to be a bit confusing. It is difficult for me to make you see this procedure in a simple manner. But once you solve a practical linear programming problem, then you will be easily be able to visualize that okay, whatever I was saying in algorithm, it makes sense and you can easily solve it. So just bear with me for another 5-10 minutes, and I'll just complete this algorithm and this will give you a good picture how we solve that. And in the next class we'll solve an example and this will give you a good understanding how exactly this algorithm works. So what we do, we actually first set the basic and non-basic variables. Again, non-basic means the variables which are fixed and basic means variables which are free to move, right? So how do we choose that? So what idea here is in the objective function, just see the objective function. If the objective function here Cj are the objective function coefficients of jth variable, and if the objective function coefficient is greater than zero, then fix the variable to its lower limit. If the coefficient is less than zero, then fix the limit to the maximum limit. And if it is equal to zero, then you can basically it is set as free, but just for uniformity, you can set it to the lower limit. Right. So this is the idea logic of it to set the variables at upper and lower limit. Right. Now once we fix the variables, now we know how to define the basic variables. You can calculate the basic variables by solving the m equations, because you will have n number of basic variables. You can easily solve it, right? If you solve it, and if all the variables are within limits, if all the variables are within limits, then optimal solution is obtained. If not, then you have to do some manipulations to bring the variables within the limit. So in this process, you do not consider the limits of the variable. The variables are free to go anywhere in the search space. So they are free to move while solving this set of solving equations, m equations. Right. Now, from the when we say that, okay, no, there is some violations, and the optimal solution is not achieved, we'll move towards some manipulation, and then we'll again calculate it and try to find the optimal solution. So that manipulation, what this algorithm has proposed, is like this. What we do is basically you have to identify the basic variable. So let's say, because basic variable was free and it can take any value in the search space. So we have to find a basic variable which has crossed its limits. So whichever basic variable has violated its limit, you have to convert that basic variable into a non-basic variable. And whenever I say limit violation, that means the one which has maximum created a maximum violation. That is the variable which we have to convert from basic to non-basic, right? And this will be obviously corresponding to some row. Just ignore this for a while, because we are going to solve it based on a matrix method. I'll show you immediately example. I'm not sure if I'll, because we are also coming to the end of the class, but we'll see in the next class, then row this. You can just see this algorithm for a while on your own, and you will get the idea. And then probably in the next class, I'll tell you more about the solution. And once you identify the row, then you have to select the variable which will. So once you have identified, okay, basic variable which will be converted to a non-basic set. Now you need to identify one variable from non-basic which will be converted to a basic variable. So that you have to do, because you have to always ensure number of variables has to be equal to number of equations. Then only you can solve that. Otherwise, you will not be able to solve it, right? So if you are shifting one of the basic variable into a non-basic set, you again have to shift one non-basic variable into a basic set. And the idea is you will take the ratio of the cost coefficient of that variable, which for all the variables among the non-basic set, and with respect to its coefficient in its original equation or equation in the rth row. This is going to be a bit difficult. I'll explain you using an example that will make things very simple. And whichever violation has taken place in the non-basic set, you have to see if the violation is on the minimum limit or the maximum limit. Based on that, whichever ratio is minimum, you have to choose that non-basic set value, and you have to bring that in a basic set. So this is the logic where we transfer or exchange the variable from basic set to non-basic set and non-basic set to basic set. And while taking these ratios, you have to understand that the ARC, because we are dividing this ARC here, so ARC should not be equal to zero. So A was the coefficient of a variable in the constraints, right? And C was the coefficient of variable in the objective function. So just for your information. And ratio should be non-negative, right? It should not be negative value. If more than, because there could be a situation if there are more than one variable satisfying these conditions, so you can choose any one and proceed. So there is no hard and fast here. You can choose any one and you can proceed for solution. And then once you actually identified these R and C values, rows and column, then you have to decide the row or divide the or multiply the row by 1 by ARC, and that row is a pivot row. And you basically for rest of the rows, you will multiply it by AIC and subtract AIJ equal to AIJ minus AIC into ARJ. This is going to be a bit difficult to visualize. I can easily understand, but yeah, just wanted to show you the algorithm before I solve the actual problem. And this repeat the previous step for the objective function also. Just subtract the objective function coefficient with a dash rj. A dash rj is nothing but this is nothing but 1 by arc. So this and this are the same value. And then again go back to step one and then solve it. If all the basic and non-basic variables are within limit, then optimization solution is achieved, or else we'll keep on iterating it till the optimization solution is achieved. Right. So yeah, this is the iteration and repeat until optimal solution is found, and we can have different variables having violations. So in every iteration, there can be different variables which can violate, and we have to ensure that none of the variables are violating. Right. So with this, let